Welcome to The Explainer. Today, we're doing something really exciting. We're going to walk step by step through an absolute mathematical masterclass. We'll be looking at exactly how the Adelic Langlands program demystifies one of the most stubborn, infamous mysteries in all of math, the Jacobian conjecture.
All right, let's dive right in. To really grasp this, we need to ground our tutorial in a few key concepts: global spectral rigidity, Galois representations, and what we call the mathematical divergence of dimensions. Basically, we're looking at how a math problem behaves completely differently, depending on whether we're operating in 2 dimensions or moving into 3 and above. We're going to explore exactly how this specific framework gives us a super powerful structural pathway to a proof by passing geometry through an Adelic sieve.
Think of this as our masterclass syllabus for today. First, the Jacobian conjecture divide. Second, the fiber polynomial engine. Then we'll evaluate the sheet collapse, explore the unipotent boundary vortex, and finally wrap up with the 2-dimensional vice.
All right, part 1, the Jacobian conjecture divide.
Now, our entire premise here relies on what I like to call a mathematical crime scene. If you look at dimensions 3 and higher, which are represented over on the left, we have this thing called unipotent drift. It's a situation where unbounded degrees of freedom actually allow mathematical defects to drift freely right to the boundaries. And, that's exactly how a counterexample was found for 3D. But in 2D, it's a totally different story. We get trapped in a highly rigid modular vice. The polynomials map precisely to modular forms of weight 2 on a GL2 background. It is locked in.
So to actually prove the 2D conjecture, we've got to hit 3 structural milestones. First up is spectral projection filtering, which we use to isolate the automorphic representations. Second, we have trace alignment verification. This is where we have to match our Hecke eigenvalues perfectly to our Galois traces. And finally, the knockout punch, anomaly quenching. This literally forces any potential mathematical friction down to absolute zero. Moving right along to part 2, the fiber polynomial engine.
Okay, this is where the algebra gets truly beautiful. Check out the fiber polynomial equation right here. Do you notice that CT cubed term? Well, that's our internal coordinator. It models the distinct sheets of our non-invertible cover. Now here's the crazy part. When this discriminant locus hits 0, those sheets merge together. The coefficient c completely drops out, the polynomial degrades, and all those missing preimages just escape along unipotent trajectories straight out to infinity.
Now, to keep this live calculation tractable, without the math just blowing up in our faces, we have to introduce a really simple but incredibly powerful regularizing coordinate. We set u equals 1 plus x times y. It's a neat little trick to collapse the system.
And that substitution gives us our exact, precise constraints. On the top, constraint 1 maps our target values, a and b, into a neat linear combination. Right below that, constraint 2 isolates our z variable in terms of our brand new parameter u and target c. These 2 master equations are literally the engine governing how our curves intersect.
Let's get into section 3, evaluating the sheet collapse.
Let's actually apply those equations to a known collision target point. So a is -1/4, b is 0, and c is 0. If you track the coordinate trajectories here, you'll see the math splits into 2 distinct branches. Branch 1 gives us our trivial base root. But look at branch 2 on the right. It yields a double root where u equals -1/2, branching into 2 more physical coordinates. Just think about what this means for a second. You are seeing the explicit arithmetic of a 3-to-1 collapse. 3 distinct source states are becoming one single macroscopic point, and it does all this without blowing up the local Jacobian determinant. It's wild. So the crucial takeaway here is that locally, the space-time feels totally flat and regular. It's what mathematicians call a smooth, unbranched E-tail map. But globally, it's secretly a multi-sheeted shadow. You see, the branching doesn't happen where we can observe it. It pinches at the unachievable boundaries of the arithmetic universe. It pinches at infinity.
Which brings us to section 4, the unipotent boundary vortex. To understand where that missing topological charge actually goes, we have to use something called a logarithmic gauge connection. Basically, this transformation takes our static companion matrix and lifts it into a highly dynamic geometric operator over the projective line. It maps our scalar algebra problem directly onto the continuous analytic parameters of a Galois representation, and it specifically targets the exact singularities where our sheets merge together.
Once we have that dynamic operator set up, we can look at its monodromy, which is really just a fancy way of saying how the data channels twist. Look at how the S3 matrices swap here. The local loop matrix right in the middle keeps sheet 1 completely fixed, but it swaps sheets 2 and 3. Meanwhile, the matrix on the far right, the global infinity loop, forces all three data channels to cycle simultaneously. And that is all because of the asymmetric scaling happening at the boundary.
Now let's take a look at the limit as c approaches 0. That's the exact moment of collision. The gauge transition forces the infinity residue into this n-infinity matrix. Notice the zeros on the diagonal? That makes it a strictly nilpotent matrix. That basically means if you multiply it by itself enough times, it just zeroes out. And because it cubes to 0, it forms a perfectly stable unipotent monodromy vortex right at the boundary. The map itself doesn't break, it just stores the anomaly as a vortex out at infinity.
Finally, we arrive at Section 5, the two-dimensional vice.
As we just saw, in Dimension 3, unbounded degrees of freedom permit that unipotent drift right to the boundary. But we are trapped in a direct mathematical vice when we drop down to Dimension 2. You see, the rigid modularity of GL2 spaces, which is dictated by the Tenyama-Shimura-Will theorem, acts like an ironclad vice. It simply cannot tolerate isolated topological defects on the boundary. So what happens? It instantly quenches the unipotent anomaly, forcing the Swan conductor, which is essentially our mathematical measure of this localized friction or wildness, to completely vanish to 0.
And the Riemann-Hilbert correspondence proves this cleanly. Any phase defect is securely locked within the arithmetic boundary as a highly structured, chaotic, or what we call a wildly ramified sheaf. But because our 2D vice forces that defect to 0, that wildness is mathematically impossible. Therefore, any 2D map with a constant Jacobian absolutely must be globally invertible. The anomaly is completely quenched. The conjecture is protected.
Understanding this whole mathematical architecture leaves us with a truly profound physical question, one derived straight from Lagos field theory. Think about it. If math proves that a 3D space can perfectly hide a global topological fold just by pushing the defect to an uncompensated boundary at infinity, well, is the flat space we experience every single day merely a localized illusion? Are we actually living in a deeply folded, multi-sheeted quantum reality, entirely oblivious to the unipotent vortices swirling at the edge of infinity? It's definitely something to think about. Thanks for joining me for this explainer.